Hello friends, welcome to my YouTube channel. My name is Prathmesh. Without wasting our time, let's begin. And if you like, please like, share, and subscribe.
Anyone who has attempted to create a narrative film using AI has slammed into the exact same wall. You generate an incredible character, set them in motion, and within 2 seconds, their face melts, their jacket turns into a backpack, and they dissolve. This instability is called latent space drift. Generative models do not possess a true understanding of 3D space or object permanence. They guess pixel values frame by frame, and over time, those guesses drift away from your original intent. The amateur response to this problem is brute force, endlessly tweaking text prompts and hitting generate 100 times in hopes of catching a lucky, cohesive 5-second clip. But professional production requires strict, repeatable continuity. If you cannot lock down spatial and temporal consistency, multi-shot cinematic storytelling is mathematically impossible. A scene cannot cut from a wide shot to a close-up if the protagonist's biometric data resets between the cuts. Multi-clip sequences generally collapse at 2 distinct failure points: the hallucination of the character's physical features and the complete reset of the environmental background. True visual consistency is never an accident. To achieve it, creators must abandon simple text-to-video generation and engineer a deterministic, multimodal pipeline designed specifically to trap the AI's predictive engine. Overriding generative randomness requires a highly structured 3-step architectural pipeline. You have to restrict the model's freedom to hallucinate at every level of the generation process. Executing this requires specific infrastructure. Models like Seeadance 2.0, easily accessible in India and elsewhere through aggregator platforms like OpenArt, are built expressly for this level of structural control. The foundational requirement here is multimodal processing. In this specific context, that means simultaneously feeding text, reference images, and base video data directly into the generation matrix to forcibly constrain the final output. The pipeline operates on 3 sequential pillars. First is spatial grounding, locking the exact physical geometry of the character. Second is temporal micro-sequencing, exerting total control over the physics of motion across time. Third is recursive video inputs, guaranteeing environmental continuity across multiple camera cuts. By layering these 3 distinct constraints sequentially, creators can drastically reduce the variance of the AI, pulling the output away from random generation and toward the predictability of a structured rendering environment. Before a character can take a single step, their physical coordinates must be hard-coded into the model. Providing a single generic reference image usually fails. When a model tries to interpret one image, it tends to blend the subject's features with the background noise of that photo, erasing highly specific micro-details, like eyeglasses, a distinct hairstyle, or a specific facial scar. The solution is a tactic called variable isolation. Instead of one broad reference, you split the character's identity across multiple, highly specific image nodes. Node 1 is strictly dedicated to facial geometry. Its only job is to provide exact biometric mapping, ensuring the face structure and specific features like eyewear are perfectly retained. Node 2 operates completely independently of the face. It isolates the external asset layer, defining the specific cut of a costume or the intricate details of a piece of custom armor. Using explicit prompting syntax, labeling inputs at image 1 and at image 2 forces the model to composite distinct wireframes into a unified, locked character model. Look at the sheer visual density of this crowded street. The tangled overhead cables, the dozens of pedestrians, the complex storefront geometry, rendering this environment requires a massive amount of computational power from the AI. If your character is loosely defined by text, the model will cannibalize their data to calculate the heavy background, causing the character's face to warp. The dual image anchor firmly reserves the compute necessary to keep the subject intact. This intense spatial grounding acts as an unchangeable visual skeleton. The character remains perfectly preserved, regardless of how complex the environment around them becomes. But locking the spatial skeleton does not solve the challenge of motion. Diffusion models frequently fail catastrophically when calculating complex physical interactions, like hand-to-hand combat or someone falling to the ground. This happens because standard text prompts ask the AI to calculate 15 seconds of dense, overlapping physical interactions all at once.
The model suffers computational overload, resulting in extra limbs, merged bodies, and physics-defying contortions. This requires the second pillar of the pipeline, chronological micro-sequencing. Standard paragraph prompts are useless for complex motion. The instructions must be physically segmented and aligned chronologically to a timeline. Look at the first sequence block. By explicitly confining the action of running to seconds 1 and 2, you restrict the AI's predictive burden. It only has to calculate a sprint for those specific frames. Moving down the timeline, you instruct the model to calculate the next physical collision only after the previous action resolves. This prevents the system from trying to render a sprint, a fall, and a block simultaneously, which eliminates overlapping physics errors. This linear pacing forces the AI's generative physics engine to respect gravity, weight, and realistic momentum. The end result of this constraint is incredibly realistic, high-fidelity physical interaction. The characters smoothly engage in complex strikes without their limbs merging. By dictating the exact second an action occurs, creators eliminate the latent space's freedom to hallucinate, forcing it onto a track of linear, realistic physics. Even with locked characters and linear physics, creators eventually hit the ultimate bottleneck, transitioning from clip 1 to clip 2. A true cinematic sequence requires multiple distinct shots occurring in the exact same location, and this leads directly to the reprompting fallacy. Amateurs attempt to generate the next shot by re-uploading the original source images and writing a slightly modified text prompt. This fails every single time. The model treats the new text prompt as a completely blank slate. It regenerates the background lighting, the camera angle, and the architectural layout from scratch, entirely destroying the continuity you just built. The professional solution is Recursive Video-to-Video grounding. Instead of feeding images into the matrix, you feed the completed video file of clip 1 straight back into the input node. The AI physically inherits the spatial dimensions, background architecture, and the precise state of the character directly from the final frame of the previous clip. Look at this wrestling arena viewed from a high angle, surrounded by thousands of unique audience members. Generating a second camera angle here using only a text prompt causes the model to scramble the ring geometry and completely redistribute the crowd. It is an absolute instant continuity error. Recursive inputs bypass this completely by acting as an environmental safe state. Because the model no longer has to calculate where the characters are, it can focus 100% of its compute power on computing the next action they take inside that locked space. Feeding output video back in as input data is the only reliable way to build complex, multi-shot narratives. It bridges isolated AI clips together into cohesive, continuous cinema. When viewed from a distance, these aren't isolated software tricks. They form a single, cohesive engineering ecosystem. This is the core formula for AI continuity. Multi-image anchors lock spatial geometry, chronological timestamps lock the physics engine, and recursive video loops lock the environment. Data moving through this pipeline produces a deterministic output. Every element is placed intentionally, bound by strict constraints. Running these multimodal, highly recursive workflows requires substantial compute capacity. This is why utilizing aggregator platforms like OpenArt to access powerful models like Seeadance 2.0 has become the industry standard for professional work. This structural approach shifts the role of the text prompt. Relying on descriptive adjectives alone is no longer the most efficient way to achieve professional-grade results across a series of shots. High-fidelity AI video production now requires the skills of a pipeline engineer, someone who can manage latent data flows to ensure consistency through every frame. The next time you sit down to create a multi-shot sequence, abandon the blank text box. Apply this precise 3-step recursive architecture to your inputs and experience the shift from experimental generation to true production control. Mastering the architectural constraints of the latent space provides the control necessary to turn AI generation into a reliable tool for professional storytelling. This dynamic martial art sequence was rendered in just 5 minutes using a single selfie as the only character reference. Standard AI video generators often fail when the action speeds up. As soon as a character throws a punch or moves rapidly, the physics break and the face begins to morph into a generic blur. Seeadance 2.0 uses a different approach. It calculates the motion physics of a fight scene while locking the character's features to the original input. Solving the physics barrier allows a character to physically interact with their environment with consistent weight, impact, and intention. This shift makes it possible to move past random generation and toward predictable, narrative-driven scenes. To access the model, navigate to the OpenArt dashboard. In the Model Selection menu, choose Seeadance 2.0 to open the generation interface. To establish the character, upload a clear, front-facing photo of yourself. This acts as the primary facial reference for the engine to track. You can then add a second image to define the costume. For example, an Iron Man suit provides a mechanical reference for the body that is processed separately from the face. This setup allows you to use specific tags in your prompt. By labeling the photos as Image 1 and Image 2, the engine maps the facial data from your selfie onto the armor design from your second reference. Because the engine treats these images as mathematical variables, it tracks your specific features and accessories, like the frames of your glasses, even during high-speed movement. Directorial control is achieved through timeline prompting. This is a method of structuring your text to manage the action over the duration of the clip. Instead of a standard paragraph, divide your prompt into timestamps. Seconds 1 to 3, the character sprints down a street. The middle block, they slide underneath a parked car. Finally, the engine attaches armor while they remain in motion. To test these sequences efficiently, set your output to a 16:9 aspect ratio at 720p resolution. This allows you to review the motion without exhausting your credits. Timeline prompting converts the AI from a random generator into a sequence renderer, giving you a predictable path for every second of the video. To expand a short clip into a longer scene, you need to use the Video-to-Video engine. For the next shot, you do not use the original static photos. Drag and drop your newly rendered video file directly back into the input box to use it as the source for the next generation. Using the video as an input maintains the environment. The lighting, camera angles, and background architecture from the first shot remain consistent in the second. You then provide the continuation prompt. The character slides into the ring and immediately begins the fast-paced fight sequence. This video-to-video workflow provides the bridge between isolated clips, allowing for the creation of a continuous sequence with matching visuals. Generative video still encounters errors. When calculating rapid movement, you may see characters occasionally swap positions or experience slight limb distortions. To manage this, generate 3 outputs for every prompt. This provides multiple takes, so you can select the render with the cleanest physics. You should also account for audio. Since the native sound is synthesized, use prompt modifiers to adjust accents or plan to add a separate voiceover during the final edit. Review the final render. Notice how the engine holds the facial proportions and processes the impact as the character hits the ground. Predictable AI video is the result of a structured workflow. By managing the inputs and the timeline, you can direct these engines to produce high-fidelity cinematic sequences.